Okay, so let's continue on here. One little thing I want to clarify here. I usually don't use the TH diagram, so I think I might have misspoken a little earlier. There is a saturation dome on the TH plot, but it doesn't, it's qualitatively similar, but it's not exactly the same. The TH plot looks kind of like on the saturated liquid side, just like the TV plot, but on the saturated vapor side, it folds over on itself, or it curves over and becomes concave. So it looks something like this. So this part here is a little bit different than the TV plot, okay? Now the isobars look the same. So here's the isobars. So here's our high pressure inlet, P1, and here is our low pressure outlet, P2, okay? So we're at 1 bar, and we're at 20 bar up there, okay? Now P2 is a superheated vapor. So we're like right there. Well, we'll see in a minute. But presumably we're in the superheated vapor region on the P2 isobar. Okay, now the ice enthalpic, H2 is equal to H1, so a new word. Ice enthalpic means that we're moving vertically on the TH plot. We're going from a high pressure to a low pressure on the TH plot, and we're moving vertically up and down. So this is an isenthalpic process. So I'm going to write right here, I'll write it over here somewhere. Isenthalpic, brand new word, isenthalpic. Constant enthalpy. Enthalpy, isenthalpic. Isenthalpic, constant H, constant enthalpy, isenthalpic process, brand new word. Brand new word. Okay, so we have an isenthalpic process going on through the throttle valve, and that means a movement vertically on the TH diagram. Remember, the saturated vapor side of the saturation dome curves in this kind of strange manner compared to the TV and the TU plot. Okay, that's just what enthalpy does, all right? So I guess, strictly speaking, TH and TV aren't exactly qualitatively the same. You got this odd behavior on the superheated vapor side. Okay, so let's calculate the quality at state 1. Quality X1 is equal to the quality evaluated for an enthalpy H1 of 16.6 kilojoules per kilogram and a pressure P1. P1 is 20 bar. Okay? Let's check H for a saturated vapor. Let's check H for a saturated vapor at 20 bar. What is the specific enthalpy? Let's see if we are above or below it. Let's see here, pressure table, 20 bar. Specific enthalpy, 2799.5. That's for the saturated vapor at 20 bar. 2799. We are below 2799. So notice this is less than a sat vapor, which is 2799 kilojoule per kilogram. So we have a saturated mix at state 1. So this isenthalpic process, so here's state 2, and here's state 1. That's the process, an upward, a downward movement from state 1 to state 2, the isenthalpic process, and it's a saturated mix. Okay, well, that means we need to use the equation for quality. Let's see here, this is going to be equal to H1 minus H sat liquid evaluated at 20 bar divided by H sat vapor minus H sat liquid evaluated at 20 bar. By the way, new nomenclature here. This quantity, H sat vapor minus H sat liquid, this guy, it's used a lot. We use it so much, we created a new quantity, H sat vapor minus H sat liquid, called HFG. The enthalpy change from fluid to gas, HFG. So H1 minus H sat liquid at 20 bar divided by HFG evaluated at 20 bar. HFG is given in saturation tables. Okay, so let's look at the specific enthalpy for a saturated liquid at 20 bar and HFG. Saturated liquid, 908.97. Let's see, so H1 is 2716.6 minus 908 kilojoule per kilogram. H-sat liquid, 908 approximately. And then we have HFG, the enthalpy change from fluid to gas, 1890.7. 1890.7. 1890.7 kilojoule per kilogram. Turn this off. HFG, 890.7 kilojoules per kilogram. Kilojoules per kilogram cancel out. And what is our final quality? It looks like it's going to be pretty close to 90-something%. Let's see here. 2716.6 minus 908 divide by 1890.7. 95%. 0.956. Or 95.6%. Quality of the inlet wet steam, X1 equals 95.6%. Okay? So the steam comes in almost a saturated vapor. 95.6% of it is saturated vapor by mass. And then it's expanded through the throttle valve to produce a superheated vapor. And remember, the TH diagram has this curve here, okay? Has that curve. So the inlet quality for the steam X1 equals 95%, and pressure P1 is 20 bar. And the outlet T2 is 120 degrees C, and P2 is 1 bar. We dropped the pressure, and we expanded a mixture of saturated liquid and vapor to a superheated vapor, okay? So we learned how to apply the energy balance and mass balance to our first simple open flow device. A throttling valve, there's nothing going on in this valve. No heat transfer, no work. We're neglecting changes in kinetic and potential energy. Therefore, the energy balance tells us it's an isenthalpic, constant enthalpy process. Isenthalpic process. H2 is equal to H1. Inlet enthalpy is equal to outlet enthalpy. And then we established that we started with this superheated, with a saturated mix, and we expanded to a superheated vapor. Okay, I wanted to spend a fair amount of time on your first example today of the energy balance for an open system. We'll move on next time to two more complicated examples involving work producing or consuming devices, turbine compressor, or nozzles and diffusers, devices which do something a little bit more than this throttling valve. The throttling valve is isenthalpic. Take care, ladies and gentlemen.